Hello everyone, welcome back to the channel. I am Yasali Reminder and today we are going to talk about space complexity, which is one of the core ideas in data structures and algorithms. Most students focus heavily on time complexity, but space complexity is just as important because it tells us how much memory an algorithm needs in order to run. In this lesson, we are not just memorizing definitions. We are trying to understand how programs actually use memory. When we say space complexity, we are referring to the total amount of memory used by an algorithm during an execution. This includes memory for variables, arrays, objects, and even memory used internally by function calls. Instead of counting memories in bytes, we look at how memory usage grows as the input size increases. That growth pattern is what space complexity is at all. At this point, it is very important to clearly distinguish between time complexity and space complexity because students often mix these two concepts. Time complexity tells us how the running time of an algorithm changes with input size. Space complexity, on the other hand, tells us how the memory requirement changes with input size. An algorithm can be very fast but use a lot of memory, or it can be slow but use very little memory. In real-world software development, we often have to make a balance between these two. To understand why space complexity really matters, imagine running your program on your system with limited memory, such as a mobile phone, an embedded device, or even a university server that is handling thousands of users at the same time. If your algorithm uses too much memory, it may crash with an out-of-memory error, even if it's very fast. In large-scale systems, memory usage directly affects cost, performance, and reliability. That is why space complexity is not just an academic concept, it has real practical importance. Now, to properly understand space complexity, we need to understand how memory is actually used in a program. When a program runs, memory is divided into different areas. One part is the code space, which stores the compiled instruction of the program. This part is fixed and does not depend on the input size, so we usually ignore it when analyzing space complexity. Another part is static memory, which stores global and static variables. This memory is allocated once and also does not change with input size. For us, most interesting areas are stack memory and heap memory. Stack memory is used for function calls, local variables, and method parameters. Every time a function is called, a new stack frame is created. This is especially important when we deal with recursion, because recursive calls keep adding new frames to the call stack. Heap memory, on the other hand, is used for dynamic memory allocations. Arrays, objects, and data structures created at runtime are stored in the heap, and this is often where most memory is consumed. Input spaces refers to the memory required to store the input given to the algorithm. For an example, if the input is an array of size n, then the memory required to store that array grows with n. This part of memory usage depends entirely on the input size and is an unavoidable part of space complexity. Auxiliary space is the extra memory used by the algorithm apart from the input. This includes temporary variables, additional arrays, and even the memory used by recursive calls. When we analyze space complexity, auxiliary space is very important because it tells us how memory efficient the algorithm itself is. When we talk about total complexity of an algorithm, we combine both input space and auxiliary space. In the other words, total space complexity is the memory needed to store the input plus an extra memory the algorithm uses while processing that input. Just like Time complexity. Space complexity is expressed using big O notation. Big O helps us describe how memory usage grows as input size increases, while ignoring constant factors and lower order terms. For example, if an algorithm always uses a fixed number of variables regardless of input size, we say its space complexity is O1, which means constant space. If the algorithm uses an array whose size depends on the input, the space complexity becomes On. If it's used a two-dimensional arrays of size n by n, then the space complexity becomes On2. The most common space complexities you see are constant space, linear space, and quadratic space. Constant space means memory usage does not change with input size. Linear space means memory grows proportionally with input size. The quadratic space usually appears when we use two-dimensional data structures like matrices. Most basic data structures such as arrays, stacks, queues, linked lists, trees, and hash tables require memory proportional to the number of elements they stores. That's why their space complexity is usually On. For graphs, memory depends on both vertices and edges, so we often express it as OV plus E. Recursion deserves a special attention when discussing space complexity. Even if a recursive algorithm does not create any extra arrays or objects, it still uses memory because each recursive call is stored on the call stack. For example, in a recursive factorial function, each function call waits for the next call to return. As a result, the maximum depth of recursion determines the space complexity. If the recursion depth is n, then the space complexity is On due to the call stack. To analyze space complexity correctly, it helps to follow a clear step-by-step approach. First, ignore code space and constant static memory. Second, look at the input and determine how much memory is needed to store it. Third, identify any extra variables, arrays, or data structures used by the algorithm. Fourth, check whether recursion is involved, and if so, determine the maximum depth of the call stack. Finally, consider the dominant term and express the space complexity using big O notation. Let's consider a simple example where an algorithm processes an array of size n and uses only one extra variable. The input space is On because of the array, and the auxiliary space is O1. When we combine them, the total space complexity becomes On. So to summarize the entire discussion, space complexity tells us how memory usage grows with input size. It is just as important as time complexity, especially in systems where memory is limited or expensive. By understanding memory types, input and auxiliary space, big O notation, and recursion, you can confidently analyze the space complexity of any algorithm you encounter in exams or real-world applications. With that, we have completed our discussion on space complexity. I hope you all have a clear understanding about it. If you enjoy this video, don't forget to like, share, and subscribe. See you in the next video. Bye for now.